Good morning. Myself Neha Sharma, Assistant Professor in Computer Science and AI, Computer Science Engineering AI Department, IIMT College of Engineering, Greater Noida. Today I am going to discuss about normalization. So here are the outlines of normalization. First one is normalization, then functional dependency, then functional dependency charts, types of functional dependency, inferences rules, and closure of a set of functional dependencies, what are the various types of normalization, how to identify the normalization, and different normal forms. So the normalization concept. So basically the normalization is the process of removing the, not 100% removing, but removing or reducing the data redundancy in a particular relational database. So here first we have to know about what actually data redundancy means. Data redundancy word comes from the word redundance. The redundance means repetition of data. If the same type of data is present in multiple different location, so there are data redundancy takes place. uh, since we have to take more time to find out particular data, since the similar type of data present more than one location in our computer. So basically normalization is the process to reducing the data redundancy, and also with the help of normalization we can decompose or divide any relation more than one relation. With the help of normalization we can remove anomalies in a particular database. Next is, what are the various advantages of normalization? So if I am talking about the normalization advantage, the first one is, with the help of normalization we can remove anomalies, insertion anomalies, deletion anomalies, and updation anomalies which is present in a particular relation. It can also reduce or restructure a database. It make database more informative to the user. Next is, with the help of normalization we can preserve the dependency and the decomposition which make from for normalizing the database, which must be lossless in nature. Next is functional dependency. So what actually functional dependency means? Basically, the functional dependency is a tool to identify the normalization. So if we have to find out the different normal forms and how to do normalization, we must aware about the functional dependency. So the functional dependency is an association between the two attribute of same relational database. One of the attribute is called determinant and another attribute is known as dependent. So here, what is determinant here and what is determined? So in that case, here A is known as determinant and B is known as determinant. If A is determinant and B is determined, then we can say that A is functionally derives B, or graphically represented is A arrow B. The symbol A arrow B can be expressed as B is functionally determined by A. It means that B will be derived after finding the value of A, or we can say that B is functionally determined by the value of A. An attribute in a relational model is said to be functionally dependent if it can take only one value for a given value of attributes upon which it is functionally dependent. So let's take one example here. We have a table employee. In that table, we have three attribute: EID, name, and salary. We can also say a relation as employee. So EID and name and salary. In that case, EID is a key. Name and salary is non-prime attribute, or we can say that these two attribute is not a part of key here. So from EID we can derive name and EID we can derive salary. So we can say that after getting the value of EID we can fetch the value of name and salary. So let's take one example. Suppose we have EID 4. So for this EID 4, the corresponding name value and the salary value can be fetched out, which is Rajan, and the salary is 9,000. Suppose if I am getting the EID 1. So with this EID 1, since this EID value is unique in nature, if we have a key, or we can say that we have primary key, so the primary key property or characteristic is it must be unique in nature, or it cannot be null. So in that case, one is unique here since the repetition of one is not present or another attribute, another tuple. So from one we can find the value of name and salary, which is Salil, and the salary is 20,000. Next is functional dependency chart. So basically the functional dependency chart is a graphical representation of functional dependency among various attributes in a relation. So these are the steps. First, we have to find out the primary key attribute. So in that case, we have the primary key attribute is EID, which is present inside the big rectangle. Next is, after finding the primary key, we just put the primary key inside that rectangle. Then all the non-prime is present outside that rectangle, which is here name and salary. And then we use arrow from this primary key to non-prime attribute to derive the functional dependency. So these are the actually functional dependency chart of a table, or we can say that relation employee. Next is types of functional dependency. So we have different types of functional dependency. The first type is partial dependency and the next one is fully dependency. So the name partial represent half, not complete, half of a particular dependency. So suppose we have more than one attribute in a primary key. Let A be a non-prime attribute. So if A is not dependent on all the prime key attribute of a relation, then partial dependency exists. Partial dependency exists at that place where more than one attribute present inside a key, and that particular subset of that key represent or derive any non-prime attribute. So the partial dependency takes place. Let's take one example. Here we have a relation student having prime key attribute is roll number and game. So from roll number we can derive name, and from game we can derive fee, and both combined roll number and game we can derive grade here. So here roll number and gate combined form a key here, and the part of all this key means the subset of this key, which is a roll number and also the game, which derive any non-prime key attribute here is name and fee. So because of this, here the partial dependency exists. And what about fully functional dependency? Since roll number and game, these two are part of a prime attribute, since these two are key here, and from roll number and game we can derive grade. So in that case, the fully dependency takes place. Next is transitive dependency and non-transitive dependency. So transitive dependency is due to the dependency between non-prime key attribute. Suppose if from non-prime key attribute we can derive any non-prime, so there is transitive dependency takes place. Suppose in a relation R, if X derive Y, so it means Y depends on X. And if we write Y derives Z, it means right hand side part depends on left hand side. So Z depends on Y. Then we can write that X derives Z, it means Z depends on X. Therefore, Z is transitively dependent on X here. So any functional dependency which is not transitive in nature is known as non-transitive dependency. Means if there is a non-prime to non-prime dependency, so in that case, the transitive dependency exists. But if there is prime to non-prime dependency, so there is non-transitive dependency takes place. So non-transitive dependency exists if there is no dependency between non-prime key attributes. Let's take one example here. We have a relation student in which the prime key attribute is roll number here, and the non-prime key attribute is name, semester, and hostel. So for each semester there is a different hostel to be allotted. So here hostel is transitively dependent on roll number, as because from roll number we can derive this semester, and from semester we can derive hostel. Semester is a non-prime key attribute and also hostel is a non-prime key attribute. And as we have already know that from non-prime to non-prime there is a transitive dependency. So in that case, because of this semester to hostel, there are transitive dependency exist, since roll number indirectly dependent or indirectly sorry derive hostel here. And name is transitively dependent on roll number, as because roll number is a key, is a prime attribute, and name is non-prime attribute. Since from prime to non-prime derive, so there is a non-transitive dependency exist here. We have one more dependency, which is multi-value dependency. And in that case, here we have a relation teacher. From teacher, we have multi-value dependency on class, as because one teacher can take more than one class. Like for example, Sam. So the teacher Sam can take computer class and as well as electronics class. In the similar way, like take if a example of class. So one class can be run more than 1 days. So computer class can be run 1 days, or computer class can be run 6 days also. Similarly, mechanical class should be continue for 5 days, and one id can be allotted to a particular teacher, like Sam have id 1 2, or John have id 2 2. So there are multi-value dependency between teacher and class, and also the class and days. Since the id is unique, so there is a single value dependency. One more dependency is trivial and non-trivial. Trivial means there is not any particular use, or we have not get any useful information. So in a relation R, if x to y, so x to y is trivial if y is a subset of x. Suppose we have x and x have a, if we consider x is a set, and this set contains the element 1, 2, 3, and 5, and y having the element 2 and 3. So we can say that y is a subset of x, and from y we cannot derive any useful information, since we have already a set x in which 1, 2, 3, and 4 and 5, these 5 elements is present, and y have already the same element which x already have. So we can say this kind of dependency is trivial dependency. Here y is a subset of x. And what about non-trivial? In a relation R, if x tends to y is non-trivial when y is not a subset of x here. Next one is inference rule. So there are 6 inference rules for a functional dependency. First is reflexibility, means alpha is a set of attribute. If beta is a subset of x, then alpha tends to beta holds. Next one is augmentation rule. If alpha tends to beta holds and gamma is a set of attribute, then gamma alpha derives gamma beta holds. Next is transitivity rule. If alpha derives beta holds and beta derives gamma holds, then we can say that alpha to gamma also holds. Next is union rule. If alpha to beta holds and alpha to gamma holds, then we can say that alpha to beta gamma also holds. Next is decomposition rule. If alpha to beta gamma holds, then alpha to beta holds and also alpha to gamma holds. Next is pseudo-transitivity rule. If alpha to beta holds and gamma beta to delta holds, then gamma alpha derives delta also holds. So the rule number 1, rule number 2, rule number 3, reflexivity rule, augmentation rule, and transitivity rule. These three are called RAT axioms or Armstrong axioms. RAT derives from the name reflexivity, augmentation, and transitivity. So we just keep the first letter of these three rules. Next is to identify the normal form. We must know about the closure of a set of functional dependency. So what is closure? If f is be a set of functional dependency, then the closure of f will be denoted by f plus, f superscript plus, which is a set of all functional dependency logically implied by f here. So formally, the set of all dependency that include f as well as all dependency that can be inferred from f is called closure of f. It was denoted by f superscript plus. So what are the steps to find the closure of the dependency? First, find out the set for which the closure to be find out. Then we have to check the functional dependency is present or not. Then add the element in the set which is not present. Repeat the step second and step third for every element. If the next state is equal to the previous state, then we just stop here. So we just take one example how to find out the closure of that element. We have the given dependency A derives B, BC derives D, C derives E, and CD derives F. And we have to find out the closure of A and C. So in that case, first we have to find out A and C. So we have to write A and C here. And we have to just find out from A and C what are the other other new value other than A and C we have to find out. So from A, we derive B. So I just write A, B, C. Then again, we have A, B, C here. So from A, B, and C, what are the other attributes we have to find out? So here B, C, we find B. So I just write A, B, C, and D. Then again from A, B, C, and D, or the combination of A, B, B, C, C, D, A, D, B, D. What are the other new things we have to find? So from this, what we get? We get from CD to sorry, we get C to E. So I just write A, B, C, D, and E. Then next is from A, B, C, D, and E. What are the other thing we have to find from all these five? So from CD we find F here. So we have all these attribute which is present in a relation are A, B, C, D, E, F. Again from A, B, C, D, E, F, we cannot find another new attribute. So I just stop here since the step number 4 and step number 5 is equal and the closure of AC is A, B, C, D, E, and F. Next is normalization. So I have already discussed that normalization is basically a process by which we decompose any relation into more than one relation to remove the anomalies. It is a step-by-step process and in each step is known as friend normal form. So if I am talking about the properties, first is it removes anomaly, insertion, deletion, and updation anomalies. It decompose the relation and it should be lossless in nature. It preserve the necessary dependency and it reduce the redundancy. So let's take one example. I have a relation student and we have total 7 attribute: roll number, name, age, branch ID, branch name, HOD name, and HOD phone number. So the first one is insertion anomaly. What actually insertion anomaly is? In that case, insertion anomalies means there is a problem while you are going to insert some value. So in that case, suppose if I am if we have new student, student have some roll number like 4 or 5, their name is X, age is 18, and the student registered in department. Uh, so we have to write the same value again in that case, like HOD name, HOD phone number. So this is the problem of insertion anomaly. Deletion anomaly, like student A drop after second year. So the at that time the corresponding HOD name and phone number is also deleted. And then the similar way, the modification anomaly. Suppose if I want to change at a single place, like age or name, there is some updation in a name. So we have to make updation in all that particular place. So there are two things. One is inconsistency, another is redundancy. Inconsistency is same piece of data have to be put in different plate and different location. Redundancy occurs because we put all the data into the same table, so we have to split this table into the two and remove the data redundancy and also the inconsistency. So this is the graphical representation in which we can say that if a relation is in BCNF, also is in 3NF. Like if you are in suppose if you are in knowledge park, so you are obviously is in Greater Noida. Similarly, if you are if a relation is in 3NF, then it is also is in 2NF. Suppose if you are in Karol Bagh, so you are in also Delhi and also in India. Since India is inside Delhi and Delhi inside Delhi there is a Karol Bagh. And if a relation is in 2NF, so it also will be in 1NF. So we can say that here 1NF like India, 2NF like 1NF like India, 2NF like UP, Uttar Pradesh, 3NF like Agra, and BCNF is like Dayal Bagh. So Dayal Bagh which is inside India, also in Agra and also in UP. So basically, these are the pictorial representation of normalization, and we just after few minutes practically know how this actually happened. So the normal form. So if I am talking about normal form, so there are total 1NF, 2NF, 3NF, BCNF or 3.5NF, 4NF and 5NF. Total 6 normal form in a normalization. So the first normal form. So what the first normal form? A relation will be in first normal form if domains of each attribute contains only the atomic value. It means atomicity must be present in relation. So 1NF defined to disallow multi-value attribute or composite attribute or their combinations. Let's take one example. Suppose we have a relation. So inside this relation, we have student ID, student name, and subject. So student ID 12, student name is Ritu, which um, which which having the subject data structure and DBMS. And another ID is 15, name is Deepthi, and subject is DBMS in Java. So the table, so first NF definitions says that there should not be any multi-valued or composite attribute. But inside this table, there is multi-valued, more than one value is present. So I just break the table or decompose the number of tuples, and inside each particular cell there is only one value is present. So in that case, the primary key is student ID, and from student ID, sorry, here the primary key is student ID and subject combined, and student ID derive the name. So I just break this DS and DBMS into two tuple, and the similarly DBMS and Java into the two tuple. So inside each cell there is one value is present, and which fulfill the criteria that one NF should be atomic in nature, and there should be not any case of multi-value dependency. Next one is 2NF. So what actually 2NF? 2NF is basically on the concept of fully functional dependency. If there are partial dependencies present, then we can say that there is not a second normal form exist. So if a relation is in first NF, and also there is any non-prime attribute which is fully dependent on primary key of R, then we can say that the given relation will be 2NF. So let's take one example. Consider a relation EP in which SSN, P number, Rs, E name, P location having some functional dependency. SSN P number derives Rs, SSN derives E name, P number derives P name and P location, in which SSN and P number is a primary key. So we just make the dependency from left to right. From SSN to P number drives Rs, from SSN drives ename, and the third dependency is from P number drives P name and P location. So this relation, so from this relation, the relation is not in 2NF because the functional dependency 1, 2, and 3 are. So because the functional dependency are partially dependent on primary key. Now we have to decompose these three. How we can decompose? Since we have primary key is SSN. We have primary key is SSN and P number. So every non-prime attribute must be derived with the combination of SSN and P number. Since R is a non-prime attribute and R's derived from SSN P number. So from functional dependency 1, there is no issue. The actual issue is generated as because SSN derives non-prime attribute which is ename, and P number, which is also a part of primary key, derives P name and P location. So because of functional dependency 2 and 3, there are partial dependency exists, and if there are partial dependency takes place, then we can say that the given relation will not be in second normal form. So we have to convert this in second normal form. So how we can do? We just break this into the three different table. So first table is SSN P number Rs, by which SSN P number drives Rs. Second one is SSN drives ename, and third one is P number drives P name and P location. Next one is now we can say that the given relation will be in second normal form, since every non-prime attribute is fully functionally dependent on their particular prime key attribute or primary key. Next is third normal form. So third normal form is basically based on the concept of transitive dependency. First, it should be in 2NF. So if it is in 2NF, so by default it is in first normal form. And there should not be any case of transitive dependency. It means that X must be a super key, or right hand side A should be a prime attribute. So there should be not any case of transitive dependency. So here we again take one example. In that case, the given relation will be, the given relation is not in third normal form. We have to convert this relation into third normal form. So here the primary key is SSN, and from SSN, which is a prime key attribute, each SSN can derive non-prime key attribute. But here D number is actually derived dname and d manager SSN. So here non-prime to non-prime derive, and for that case the transitive dependency exists. So uh, to convert this into a third normal form, we just break the relation into two, in which from SSN birth date, address, d number, e name is derived, and the second table from d name and d manager SSN, d number is derived. Now we can say that the given relation will be in third normal form. Next is BCNF, or the other name of this is 3.5 NF. BCNF is strictly stronger than 3NF. Every relation is BCNF if it is in 3NF. So a relation is in BCNF if and only if all the determinants are candidate key. Means left hand side should be a key. Let's take one example of a student here, which having three attribute: roll number, subject, and teacher. So a student can have more than one subject, a teacher can teach more than one subject, and a subject can be taught by more than one teacher. So there are two candidate key: roll number and subject, roll number and teacher. So relation student is in 3NF but contains some anomalies. If student have roll number 7 is deleted here like this. If I deleted 7 here, so the corresponding value is also deleted. Like uh, we deleted teacher 4, T4, and also VV group. Next, there are also insertion anomalies. Suppose if I want to add the subject VC plus plus, so I have to add one roll number and one teacher also. And also there is updation anomaly. If we want to change a teacher for a subject C, so we have to search all the subject having subjects, all the roll number having subject C, and we have to change that particular teacher here. So in a relation student candidate key overloaded, you have to find teacher by roll number subject and also by roll number teacher. So here the roll number is overloaded. So what we do, we just divide the relation into two. First one is roll number to teacher and second relation is teacher to subject. Now all the determinants are candidate key and we can say that the given relation will be now in BC. Next one is 4NF. 4NF basically depends on multi-value dependency. In that case, there are two kinds of dependency: trivial multi-value, non-trivial. Trivial means we don't get any fruitful information or useful information. So the actually focus about non-trivial. So a multi-value dependency, X multi-value dependent on Y in R is called trivial if Y is a subset of X and X union Y is equal to relation R. Otherwise, it is non-trivial is in relation. If y is not actually present in the x, or the subset the value which is present in y is not equal to the value which is present in x or not connected to x, then we can say that there is non-trivial dependency. So a relation schema R is said to be in 4NF if and only if every multi-value dependency x multi-value dependent on y holding R, if it will be in 3NF and there should be trivial multi-value dependency, and every non-trivial multi-value dependency X should be a super key of R. So let's take one example here. The relation R is not in 4NF because non-trivial multi-value dependency employee to skill takes place. Since Deepti also read Java and Ritu also read Java and Deepti also read C. So Deepti read more than one skill. So from employee to language and employee to skill. Employee is not super key here. So we decompose the relation R1 and R2. First, employee and skill, one table, and second, employee to language, second table. Now we can say that employee to skill in R1 and employee to language in R2 are trivial multi-value dependency, and the relation will be in 4NF. And the next one is fifth normal form. Fifth normal form is basically related to joint dependency. A joint dependency denoted by R1, R2, R3. According to the joint dependency, every legal state of R should have a lossless decomposition. That is phi of R1, R2, or we can say that projection of R1, R2, and R3 up to Rn should be equal to R. So we have a relation S, P, and J in which we have four tuples. And first we divide it into two parts, SP and PJ. And if I combine SP and PJ into SPJ, so I just get one more tuple which is highlighted here by yellow color. And because of this tuple, there are joint dependency exists, and if a relation having joint dependency, then we can say that the given normal form will not be in fifth normal form. So because of this dependency, this tuple is actually a extra tuple, since the in original table we have four tuple, but after joining, after decompose the table and combining these two, because of joint dependency, there are one more extra tuple, and this tuple is known as spurious tuple. So we have to, so our aim is actually here to remove this particular tuple. So what we do, we just take these S and J, and now we again divide the table SPJ into three parts. The first part is SP, the second part is PJ, and the third part is SJ. And after combining these three, we again get the original value, which is having the four tuple, and inside this again we have four tuple. So now the decomposition is lossless, and we can say that the given relation will be in fifth normal form. Let's discuss some of the numerical on the basis of normalization. So first we have a relation R is given, and we have four dependency. So we have to find out whether the given relation is 1NF. So I just start from the highest normal form like BCNF. So BCNF says all left hand side should be key here, and in that case the left hand side all the dependency is not key. So BCNF fail. And if I am talking about 3NF, so the 3NF says that either there should be a key on the left hand side, or right hand side there will be a prime attribute. So 3NF fails. Then if I am talking about 2NF, so there should be a partial dependency, since if AB is a key, so the subset of key which is A derive non-prime attribute which is I. So the given relation will be in 1NF, and I just break right hand side attribute into one parts, yeah, like BD derived E, AD derived G, BD derived F, AD derived H. Next one is here BC derives ADE and D derive B here. So we have to identify whether the given relation will be in 1NF or not. So we can say that the given relation will be in 1NF as it fulfills all the criteria, and right hand side should be a single attribute. We just break, decompose. Next one is relation V, W, X, Y, and Z. X derive Y, Y derive Z, Z derive Y, and W, V derive Y. So X, Y, Z. In that case, all these three are keys. But W, V derive Y. This is not actually key. X, Y, Z is a key. But right hand side should be a prime attribute. So the given relation will be in 3NF, and if a relation will be 3NF, it also is in 1NF. Next one is relation A, B, C, D, E, and F is given. So we have total 5 dependencies here. So first we have to find the candidate key. After finding the candidate key, uh, put we have to put all the criteria which is in BCNF, 3NF, 2NF, and 1NF. And if it satisfy all the criteria, so we can say that the given relation will be in that particular normal form. So the given relation in one normal form, because it will not satisfy BCNF, 3NF, or 2NF criteria, since there is transitive dependency or partial dependency also exists. Next one is we have a relation A, B, C. A derives B, B derives C, and C derives A. So we have to identify whether the given relation is 3.5 NF or bisecode normal form. So we can say that if we have a single key present, and from single key we can identify non-prime attribute, and all the left hand side there should be a key, since from A we can derive B and B to C. Again, if we find the closure of B, from B we derive C, and from C to A. And if we find the closure of C, so from C we can derive A, and A we can derive B. So A, B, C, all these three are keys. So we can say that the relation R will be in BCNF. Next one is relation R A, B, C, D, and from AB derive CD and D to A. So AB is a key here, because AB to we derive CD, and from A, B, C, D we have total number of attributes. D is non-prime attribute, but non-prime will not derive non-prime. Non-prime is actually derive A, which is a part of key here. So the given relation will be in 3NF. Thank you.